Now we are going for third subtopic of the electrostatic, which is electric potential. Before we discuss the electric potential, I want to discuss the electric potential energy U first. So what is the electric potential energy? It's a form of energy related to the position of an electric charge in an electric field. So U is given by U equal to K capital Q, Q naught over R. So, commonly the capital Q we refer to point charge. A symbol of capital Q is for point charge, and the symbol of Q naught we refer to test charge. So from here, U is the electric potential energy, Q and Q naught is the charges. When you do the substitution in the equation, you must include the sign of charge. And then R is the distance between test charge and point charge. The K is the electrostatic or Coulomb constant. And the U is a scalar quantity. SI unit of the U is a joule, or you can use a symbol capital J. Now we are going to the electric potential. We use a symbol of capital V. So what is the electric potential? Electric potential of a point in an electric field is defined as the potential energy per unit positive charge at that point in the electric field, and it given by V is equal to U over Q naught, or is defined as the work done per unit charge in bringing positive test charge from infinity to that point in the electric field, and given by V is equal to W infinity over Q naught, where Q naught is a value of a test charge. In the calculation, you must include the sign of charge. Electric potential is a scalar quantity. SI unit of the electric potential is volt, or you can use symbol capital V, or joule per coulomb. And then another equation of the electric potential, or we call it as derived equation of the electric potential, which is V equal to K capital Q over R, where Q is a value of a point charge, means that when you substitute in the you do the calculation, you must include the sign of charge. And then R is the distance between a point and point charge. So how we get the V is equal to K capital Q over R? It comes from the equation of the definition of electric potential just now. V is equal to U over Q naught, and U is equal to K capital Q naught over R. So we combine this equation, it becomes V equal to K capital Q naught over R over Q naught, and then finally it becomes K capital Q over R. So from this equation, the capital Q refers to point charge. From the equation of the electric potential you learned just now, which is V equal to U over Q naught, then V equal to W infinity over Q naught, and another one V is equal to K capital Q over R. So the electric potential can be positive, negative, or zero, depend on the sign and magnitudes of capital Q, Q naught and W infinity. So W refer to negative or positive. If the work done is positive, means that work done by the external force or on the system. If the work done is negative, means that work done by the electric force or by the system. From here, don't forget, in any calculation involving of U, W and V, the sign of charge must be substituted in the related equation. Now I want to discuss the equation of U equal to Q naught V. It comes from equation of V equal to U over Q naught. And we rearrange for this equation, become U equal to Q naught V. I want to compare the value of U if I use the positively and negatively charged particle in the equation. So first, if the positively charged particle used, so the electric potential energy of a positively charged particle increases when it moves to a point of higher potential. While if the negatively charged particle used, so the electric potential energy of a negatively charged particle increases when it moves to a point of lower potential. So how can this happen? Let me show you using calculation so that you will more understand on this statement. We go for the positively charged particle. So let's say Q naught, we use Q naught positive 2 microcoulomb and V1 is 2 volt, while for V2 is 4 volt. The 2 volt is a lower potential. Okay, while for V2 is high potential. Then we substitute in the equation of U equal to Q naught V just now. So we label it as U1 equal to Q naught times with V1. So we substitute with the value. And then we will get for the U1 with low potential, which is 2 volt, we will get the 4 power of negative 6 joule. Okay, while for the U2, Q naught V2, so we substitute the value with 4 volt, which is high potential, we will get 8 power of negative 6 joule. From this substitution and the value, you will see that U1 is less than U2. So from this calculation, show that the electric potential energy increases if it moves from low potential to high potential. Okay, while for the negatively charged particle, okay, let's say we use the Q naught is negative 2 microcoulomb. Okay, and then the V1 2 volt, which is low potential. Okay, and then V2 is equal to 4 volt, which is high potential. Same like the positive charged particle just now. So we substitute with U1, Q naught V1. We substitute with the negative times 10 to power 2 times power of negative 6, and we times with the low potential. For V1 is 2 volt. We get the negative 4 power of negative 6 joule. And then for the U2, we substitute for Q naught times with V2 and negative 2 microcoulomb charge, and times with the high potential just now is 4 volt, and the value we will get negative 8 power of negative 6 joule. If you see these two values between the U1 and U2, you can see that value of U1 is more than U2, which is U at low potential is more than U that from the high potential. So that from here we can conclude that electric potential energy of negatively charged particle increases from low potential to high potential. Let's take note here that total electric potential at a point in space is equal to the algebraic sum. So let's see the example here. Let's say a point charge Q1 negative 2 microcoulomb, and then second point charge is Q2 positive 5 microcoulomb, and we have a point here. Let's say we label it as point A. So from point charge Q1 to point A is, let's say, 1 meter, and then Q2, point charge Q2 to point A is 2 meter. So the total electric potential at point A equal to electric potential from point charge 1 to point A, and then plus with electric potential from point charge Q2 to point A. So it becomes KQ1 over R1 to point A plus KQ2 over R2 to point A. So when we do the substitution, it becomes 9 times 10 power of 9, and then the Q1 just now is negative, so you must insert the sign of charge into substitution. So negative 2 times 10 power of negative 6 over the R is the distance between point charge to a point. Okay, so distance between the point charge Q1 to point A is 1 meter. We put it 1, and then plus the Q2 is positive, so we put it positive 5 times power of negative 6, and the distance Q2 to point A is 2 meter. Put it 2. So this is how you total up the electric potential at a point. Next one, the theoretical zero of electric potential of a charges is at infinity. If you see the equation of V equal to KQ over R, so when at infinity, R is infinity, so the V become KQ over infinity. So any value over with infinity will equal to 0. So theoretically, electric potential will 0 at infinity.